Why auto mode is the most expensive button in your house. You pressed one button. The machine beeped. The LED display lit up. And then, the machine decided to execute multiple additional steps you never asked for. Look at this button. It is on the control panel of your washing machine. It is on your dishwasher. It is on your air conditioner. It usually says Auto, Smart, AI, or Sense. For most users, this is the default setting. You press it because it implies intelligence. It implies that the machine is scanning the load to calculate the perfect balance between performance and resource usage. You believe it is saving you water, electricity, and time. Mechanically, you are wrong. When you press Auto, you are not asking for efficiency. You are asking for a safety margin. And in the world of engineering, safety margins are expensive. In this video, we are going to expose the hidden logic inside your appliances. We will break down the control algorithms that govern that button. We will show you why sensors lack context, why the code defaults to conservative settings, and how this safe choice quietly adds mechanical wear to your machine and cost to your bill. This is the invoice for not thinking. To understand why auto mode creates waste, you have to look at the system logic. When a modern appliance runs in auto mode, it relies on sensors to make decisions. However, these sensors provide raw data without context. And when data is ambiguous, the algorithm is programmed to prioritize reliability over conservation. Take the washing machine as our first example. When you select Auto, the machine relies on a turbidity sensor to determine the soil level. This optical device measures how easily light passes through the drain water. If the water is clear, the logic assumes the load is clean. If the light is scattered, the logic assumes the load is dirty. This mechanism works in a controlled lab, but it encounters variables in the real world. For instance, if you use a detergent that creates significant foam, or if the water chemistry causes cloudiness, the sensor detects light scattering. It cannot distinguish between soap suds and actual dirt. Faced with this ambiguity, the system defaults to the higher requirement to ensure performance. It interprets the signal as heavy soil. Consequently, it triggers a correction protocol. It may initiate a fresh water refill. It may engage the heater to maintain temperature longer. It may extend the agitation phase. It may add an entire extra rinse cycle. From your perspective, the clothes were likely already clean. But the machine's logic dictates that it must eliminate the possibility of a poor result. It consumes additional resources to solve a problem that may not exist. This is the definition of a safety margin. Let's move to the dishwasher. Auto mode, often labeled sensor wash, uses a similar optical analysis. It continually adjusts water temperature and cycle duration based on particle detection. Consider the false positive scenario. Some food residues, like tomato sauce or starch, are highly opaque. Even a small amount can cause a sharp drop in sensor readings. The sensor reports high opacity. The computer responds by switching to a higher intensity profile. It increases the water temperature to the upper range of the cycle. Heating water is the most energy-intensive part of the operation. It increases the spray arm pressure. It extends the wash duration. You are effectively running a heavy-duty cycle for a standard load. You chose smart, but the machine chose maximum certainty. The most critical example is your air conditioner. This is where the cost implications are significant due to the nature of compressors. Modern inverter ACs are designed to be efficient by running at steady, low speeds. However, auto mode often prioritizes responsiveness over steady-state efficiency. To understand this, we need to look at the PID control loop. Proportional integral derivative. This is the algorithm used to correct the difference between the current room temperature and your target. In manual mode, setting a fixed fan speed and temperature, the system tends to ramp up gently and settle into a consistent, low-power operation. This is linear and efficient. In auto mode, the system often creates a more aggressive feedback loop. If the sensor detects a temperature deviation, perhaps due to a person entering the room or a shift in sunlight, the controller calculates a requirement for immediate correction. It commands the inverter compressor to ramp up rapidly. The compressor accelerates. The electrical amperage rises to overcome inertia. It delivers a burst of cooling to neutralize the error quickly. Often, this rapid response leads to overshoot, where the room becomes cooler than the target. The system then cuts power to the compressor to compensate. Later, it restarts the process. This behavior is known as hunting. Instead of a smooth line of energy consumption, the system draws power in spikes. Physics dictates that an electric motor is most efficient when it maintains momentum. Accelerating a mass requires more energy than keeping it moving. By constantly adjusting, the system spends more time in its acceleration phase. But the electricity bill is only the first part of the invoice. The second part is invisible. It is mechanical fatigue. Machines are physical systems subject to wear. Motors have a service life influenced by start-stop cycles. Electronic boards undergo thermal expansion and contraction during current spikes. When auto mode extends a cycle, it adds runtime to the pumps and motors. When it forces the compressor to ramp up and down frequently, it increases thermal stress on the components. When it adds an extra rinse, it cycles the valves one more time. You are not just paying for energy, you are consuming the mechanical life of the appliance. Auto mode drives the hardware with less regard for longevity and more regard for immediate performance. It prioritizes this certainty of result today over the preservation of hardware tomorrow. So, does this mean you should never use auto? No. Auto has a purpose. It is useful when the variables are unknown or widely fluctuating. It serves as a reliable backup. But for consistent daily use, you can optimize the outcome. Here is the protocol to reduce the safety margin tax. Step 1. The learn and lock method. Use auto mode once as a diagnostic. Observe the final settings it selects. Does it choose a high spin speed? Does it choose multiple rinses? Now you know the machine's safe baseline. Next time, switch to manual mode. Dial in similar settings, but step down slightly. Reduce the rinse count by 1. Lower the spin speed 1 notch. The result will likely be indistinguishable, but the excess consumption is removed. Step 2. Utilize normal or eco cycles. On washers and dishwashers, standard cycles like normal or eco are often the most strictly regulated. In many regions, these are the cycles used for energy efficiency certifications. The algorithms for these cycles are tuned for conservation. Auto cycles are typically exempt from these strict profiles, allowing them to use more resources to guarantee performance. Eco may take longer, but time costs nothing. Mechanical work costs money. Step 3. Stabilize the system. On your AC, select a specific mode like cool or dry. Select a fixed fan speed, low or medium. Prevent the machine from constantly adjusting the fan. Force the system to run steadily. Consistent operation is the key to efficiency. We have been trained to believe that newer means smarter. We assume the microchip understands the context of our home better than we do. It doesn't. It understands algorithms. It understands how to minimize the risk of a poor result. It understands how to ensure the job gets done, regardless of the cost. Auto is a luxury setting. It buys you the luxury of not deciding. And like all luxuries, it carries a premium. The machine isn't smart. It is cautious. And caution is expensive. Next time you reach for that button, pause. Ask yourself, do I need insurance? Or do I just need the machine to do its job?